I thought it would be useful to make a primer video on differential equations, in particular second-order differential equations, and how they apply to mechanical vibration problems. I've found that a lot of times people studying this material really struggle with connecting the math with the physics. So I thought I would give a little bit of a tutorial on that. The form of the equation that we deal with in these problems is mx double dot function of time plus cx dot of t plus kx of t is equal to some general function of time f of t. We'll call that equation 1. I should also mention that m, c, and k are all positive, and they're real. In fact, let me underline that in red just to make the point. Right? Since this is a second-order differential equation, we end up with two constants of integration. You can imagine that if this rest of the equation wasn't here, and I integrated mx double dot twice, I'd end up with two constants. So in order to uniquely specify the solution, we need two initial conditions. Now, in the course of studying differential equations, you might have heard these described as boundary conditions because you might have looked as y as a function of x. In this case, we call them initial conditions because x is a function of time. So what happens initially means this is the state of the system at time equals 0. So initial conditions and it says something like at time equals 0, the displacement of the system is known, so we'll call that x, or the state of the system. X of 0 is equal to some quantity, some constant called x0. And also at time equals 0, we know the velocity, which means that x dot, the time derivative of x at 0, is some known constant which we'll call x dot 0. And we'll call these equations 2 and 3. Now you might remember from your math classes, your calculus classes, that the solution to equation 1 has two parts to it. So the total solution, which I'll just call x of t, is the sum of the homogeneous solution, which we can call x sub h of t, plus the particular solution, which we'll call x sub p of t. Call that 1, 2, 3, 4. Okay. So initially what we need to do is find the homogeneous solution, and we find that by setting the right-hand side, or the function f of t, equal to 0. So let's write that down. The first thing we tackle is the homogeneous solution. And we do that by setting f of t equal to 0. Now, in mathematics, we call it the homogeneous solution. In mechanical vibrations, we refer to this as the free vibration problem. Why? Because there's no force on the right. And the solution to the free vibration problem. So the solution to the free vibration problem gives what's known as the transient response of the system. Let's write that down too. Transient response. What it's telling us, the transient response or the free vibration problem, is what does the system want to do in the absence of any external forces? What is the nature of the system? So let's have a look at how we solve that first. So I mentioned we set f of t equal to 0. We call that 5. Therefore, we can rewrite equation 1 as mx double dot plus cx, and I'm leaving out the dependence on time here. Should be implied that x is a function of time, but just for shorthand, to keep it compact, I'm just going to write it as x. This should be x dot cx dot plus kx equals 0, and this is equation 6. And the idea is we want to solve equation 6. Now in equation 6, we have x and its derivatives multiplied by constants, which we've said are positive and real, and somehow those added together equal 0. So what is the sort of function that might be a good candidate for a solution? Well, it turns out the exponential function is e to the rt. Why? Because each time I take the derivative of e to the rt, I'm just multiplying by r. What do I mean by that? So x equals e to the rt, we'll call that equation 7. The derivative x dot is equal to r times e to the rt, 8. And double dot, the second time derivative, is equal to r squared times e to the rt. We'll call that 9. Now, if I substitute 7, 8, and 9 into 6, let me write that out. Substitute 7 through 9 into equation 6. We end up with, let me group it like this, mr squared plus cr plus k times e to the rt is equal to 0. And it should be fairly clear that e to the rt is never equal to 0. Right? So we can divide both sides by e to the rt. Let me just use yellow for this. So therefore, what's in the bracket must be equal to 0 to solve equation 6, or to satisfy equation 6, I should say. So this implies that mr squared plus cr plus k equals 0. And what is the r that solves it? Well, this is just the roots of a quadratic equation. So this is a very well-known solution from high school math. We know that r1, 2 is equal to minus c plus or minus the square root of c squared minus 4mk. Oops, let's erase a bit of that. Divided by 2m. Okay, so what have I done? I've taken the assumed solution, x equals e to the rt, and I've put that into equation 6 along with the derivatives, and we end up with something that we call, this is called the characteristic equation. And the solution to the characteristic equation gives you the roots, r1 and 2. They're two roots because it's a second order polynomial. It's a quadratic. And the roots 1 and 2 give you the solution that satisfies equation 7. I should actually write this here. Call that 7. We'll call this 8. All right, so let me make a little bit more room here. I'm going to choose to rewrite this as r1 and 2 is equal to minus a plus or minus b, where a is equal to minus c over 2m. Excuse me, a is equal to just c over 2m. Fix that. And we should note that a is always positive, since c and m are positive. And b is equal to the square root of c squared minus 4mk, all divided by 2m. We'll call this equation 9, 10, and 11. Okay, and now we need to consider different cases. We'll call them case 1, 2, and 3, and those have to do with what is under the square root sign. The three cases are, what if this quantity is positive? What if this quantity is 0? And what if this quantity is negative? Okay, so turning the page, what I've done is I've gone ahead and I've copied the results from the previous page here, where fundamentally we're examining the roots, and I've said that there are three different conditions, and that has to do with what's under the square root sign. Either that is positive or it's 0. So let's look at case 1. where we are positive, which is to say that c squared is greater than 4mk. And this, of course, implies that b are left. And by different, we mean distinct. All right, so in this case, we can write the homogeneous solution, x sub h of t, is equal to c plus bt plus c2 times e to the minus b times c. And where did that come from? You remember on the previous page, equation 7 is that E is equal to RE and E equal to RT. Each one is a combination of both. Now, the initial conditions might suggest that one of these constants is 0, in which case that will fall away and it will just be the other part of the solution. But each one of these, meaning each one of these solutions corresponding to roots R1 and R2, are valid solutions. Let me just write here that this is R1, this is R2, so there should be no confusion. I can take the solution and I can rewrite it as follows. This is equal to e to the minus at times c1e to the bt plus c2 times e to the minus bt. And we'll call this equation 12. If c is greater than 4x exponent multiplied by another exponential function, and this exponential function has a negative sign because a is always positive. And what happens is as time grows, as t increases, this whole function, there are times when it might not, but in general, this is going to decay exponentially. So the case 1, you end up with a response that looks like exponential decay. Something like this, if this is t and this is x. Okay? In fact, this doesn't go to 0. This would be 1. All right, I'm going to just take this away to make room. All right, that's case 1. Let me try to separate it. Case 2, in this case, c squared is exactly equal to 4mk. All right, and this implies that b is equal to 0. So if we look at the roots here, we can see that if b is 0, then the roots must be equal. So let's write that, do it in red. Roots are real and equal. All right. So in the event that the roots are real and equal, the form of the homogeneous solution looks like c1 times e to the minus at plus c2 times t e to the minus at. If you've forgotten why that is, you should go and review your calculus of differential equations. But fundamentally, it's a second-order differential equation. We need two solutions. So when the roots are equal, when one of the solutions is equal to another one, we put a t in front of one of them. I should further mention that in case 1, we call this the overdamped case. In terms of mechanical vibrations, it's known as the overdamped case. Okay, equation 2 is something we call the critically damped case. Right, and now we can have a look at case number 3. which I think is the most interesting of the three cases, which is why I've saved it for last. And in this case, c squared is less than 4mk. Okay. This implies that b let me do this here where I've got more space. So this implies that b is equal to the square root of, how do I want to write this? What I'm trying to say, it's not that b is equal to, the roots, b is imaginary. So I rewrite the roots 1 and 2 as equal to minus a plus or minus b times I. In other words, b is an imaginary number because what's in the square root sign is negative. And what we can end up doing is we rewrite it this way, where, to be clear, b in this case is equal to 4mk minus c squared square root divided by 2m. Okay, and these roots are complex conjugates. Let me do that in red. Roots are complex conjugates. So they have a real part and they have imaginary part. And the two roots, what we're adding, the imaginary part and subtracting, are exactly the same. Okay, and this is a situation that's known as underdamped, if we look at the mechanical vibrations problem. So in this case, what does the solution look like? Well, one of the ways we could write it is that x homogeneous of t is equal to c1 times e to the minus a plus b I times t plus c2 times e to the minus a minus b I times t. I could then also rewrite that as e to the minus at times c1 e to the b, let me write it this way, I times bt plus c2 e to the minus I bt. Now, if we invoke Euler's law, which says, very well-known law mathematically, said by many to be the most beautiful law in all of mathematics. I won't elaborate at this point, but that says that e to the I theta, or e to the plus or minus I theta, is equal to cosine of theta plus or minus I sine of theta. A consequence of that is that we can write cosine of theta is equal to e to the I theta, excuse me, that should be plus I theta, e to the I theta plus e to the minus I theta divided by 2. And we can also write, I'm going to squeeze it in here, that sine of theta can be written as e to the I theta minus e to the minus I theta divided by 2I. All right, so let's give these some numbers. Going back here, this would be number 13. This would be number 14. Let's just call these 15 and 16. Now, if I substitute 15 and 16 into 14, you should be able to kind of just look at it and see this, but I encourage you to do it on a piece of paper. We find that x sub h of t can be written as, excuse me, e to the minus at times C1 cosine of bt plus C2 sine of bt. Okay, I should point out, we'll call this number 17, I should point out that the constants here, C1 and C2, are not the same as these constants. I could write them as D1 and D2, but I thought that would just be confusing. So they are still constants. They're just different constants from these. So don't ever solve for these constants and then say, well, those are the same. That's all. I just didn't want to confuse the issue by changing it. So the idea is that when we have an underdamped situation, in general, we have simple harmonic motion, as it's called in the mechanical vibrations problem. We have oscillations. Sine and cosine is an oscillatory type of motion. And these are being multiplied by some term in front that, as we said before, is just an exponential decay. It's something like that. So in general, this is an oscillatory motion that is decaying. The peaks of the sine and cosine functions are decaying exponentially with time. All right, that's all I want to say in this video. In the following video, we'll deal with the particular solution, or the forced vibration problem. I hope you found something useful. If you have, please go ahead and give us a thumbs up, or better still, subscribe to the channel. Thank you for watching, and we'll catch up with you in the next video.